So let's introduce our principal agent model. The basic idea of the model is that an employer will be designing a wage contract. In our model, we will assume there are two states of the world, the good state, capital G, and the bad state, capital B. So we're keeping things very simple. The employer will be able to observe the level of revenue. So there are two levels of revenue, one in each state, revenue RG and revenue RB, the good revenue and the bad revenue, and RG is strictly greater than RB. So you can think of perhaps an employer running a shop who's going to go away for the day, and when he comes back, he can observe the amount of money in the till at the end of the day. While the employer is away, he's going to leave an employee in charge, and he's going to pay this employee according to the level of revenue that he observes. So the employer will design a wage contract, which will denote lowercase w, which has two dimensions, an amount WG, which is the amount that the employee will get paid if the employer observes a good level of revenue in the till at the end of the day, and an amount WB, which is the amount that the employee will be paid if the employer observes the bad level of revenue in the till at the end of the day. If the employee accepts the wage contract offered by the employer and comes to work for the day, we're going to imagine that the employee can choose between two levels of effort. So the employee can choose to exert a high level of effort or exert a low level of effort. Now, later on, as we study different cases of information, we're going to make different assumptions about whether this level of effort is observable. So it might be the case, under perfect information, that the employer is able to perfectly observe the level of effort by the employee. In this sense, it might even be written into the contract to specify a level of effort. Under asymmetric information, however, the employer will not be able to observe this level of effort. A key assumption that we're going to make in this model is that the level of effort cannot be deduced by observing the level of revenue. Mathematically, we would say that effort is not measurable by observing revenue. So whatever the level of effort the employee chooses, it's possible that there will be bad revenue or good revenue. Okay, so revenue is random and both levels are possible under both levels of effort. We say that revenue is stochastically related to effort in the following sense. So effort is going to affect the distribution of this random variable revenue. It's not going to determine the level of revenue, but it's going to affect the likelihood of it being bad or good. So let's make this quite clear and say that if the employee exerts a high level of effort, then the probability of bad revenue conditional on high effort is less than the probability of bad revenue conditional on low effort. So if the employee chooses to exert a high level of effort, they make bad revenue less likely and so make good revenue more likely. This is what we mean by a stochastic relationship. So let's consider the profit that the employer makes in this model. Well, the employer's expected revenue is going to be determined by the level of effort that an employee exerts. So expected revenue would be the probability of bad revenue multiplied by the level of bad revenue plus the probability of good revenue multiplied by the level of good revenue. And of course, the probability of bad or good revenue is determined or is affected by the effort of the employee. Now, because we assume high effort makes bad revenue less likely and bad revenue is less than good revenue, two very natural assumptions, we can see that the expected revenue conditional on high effort will be greater than the expected revenue conditional on low effort. So expected revenue takes one of two possible values, and the only thing that an employer can do to try and increase expected revenue is to somehow encourage a high level of effort from the employee. They will have to determine whether this is worth it by looking at the expected costs. Expected cost is quite simple to calculate and again will depend on the level of effort the employee exerts. Remember, a contract has two dimensions, a payment WB in the bad state and a payment WG in the good state. Of course, the employee chooses a level of effort which is going to affect the likelihood of the bad state versus the good state, and so affect the expected cost of the contract that the employer is using to pay this employee. So in general, the expected cost of the contract that the employer is using will be the expected value of W conditional on the level of effort. So we take the probability of the bad state conditional on the level of effort and multiply it by the wage in the bad state, and then add to this the wage in the good state multiplied by the probability of the good state conditional on the level of effort that the employee is choosing to exert, either a high effort or a low effort. So let's go on paper now and develop a graphical tool, ISOcosts, for analysing the firm's expected costs in this model. Okay, so let's examine the firm's costs a little more. This model is very similar to the Rothschild-Stiglitz model, so a lot of these techniques will feel familiar. So in general, if we have a contract W, which if we remember has two dimensions, a wage in the good state and a wage in the bad state, okay? Then if we want to calculate the expected cost of this contract, so these are payments the firm is going to make to the employee. So what is the expected cost? Well, it's going to depend on the level of effort. So we take the expected value of the contract W conditional on the level of effort, and let's put epsilon subscript I. So where I is either H or L, so either high effort or low effort. Now, to take an expected value, you just weight each of these terms by their respective probabilities and sum up. So the probability of the bad state will be probability of state B conditional on the level of effort. Okay? So this is, in some sense, the probability of observing bad revenue, which we consider to be stochastically related to the level of effort. And then we multiply that by WB plus 1 minus the probability of the bad state. There's only two states, so these probabilities sum to 1. So this is the probability of the good state, conditional on effort epsilon I, and multiply that by WG. Okay? So this is the expected cost when the firm is using contract W and the level of effort is epsilon I, either high or low effort. Okay, so when we represent these graphically, we use isocosts. And if we remember, the condition for an isocost was essentially that the expected, the expected cost of the contract conditional on the level of effort is not changing. So if I could write the differential, as in the change in this expected cost, is 0. And how does this cost change? Well, because either WB changes or WG changes. So I could rewrite this as the probability of the bad state conditional on effort epsilon I multiplied by the change in the bad state wage plus 1 minus the probability of the bad state conditional on effort level I multiplied by the change in the good state. Okay, so if we're changing the bad state a bit and changing the good state payment a bit, well, if we're on an ISO cost, the overall effect is that the expected cost doesn't change. And so we get this expression for along an ISO cost. This is not always zero. It's zero when we're looking at a particular ISO cost. And then rearranging this expression to get dWB over dWg. So we'll think of the bad state wage as the y-axis and the good state wage as the x-axis. So this is dy over dx. So the slope of an ISO cost will be the negative of this odds ratio, very similar to what we've seen before. And it depends on the level of effort. Okay? So it's minus and then 1 minus the probability of the bad state conditional on effort epsilon I divided by the probability of the bad state conditional on effort level epsilon I. So this is the slope of an ISO cost is going to change as we have different levels of effort. Okay. Now, if you remember, we had the assumption that these probabilities, the probability of the bad state conditional on high effort is less than the probability of the bad state conditional on low effort. And they're both between 0 and 1. So the bad state is always possible under both levels of effort. It's just that high effort makes the bad state more likely. Now, if you rearrange this, it could be shown that the slope of an ISO cost under a high level of effort these are steeper. Okay, so it's more negative. So this is less than 1 minus the probability of the bad state conditional on low effort. Okay, so this is what we can deduce, and essentially remembering that this slope here is more negative than this term here, so this is steeper than this, which means that under a high level of effort, ISO costs are steeper than they would be under a low level of effort. So let's just put this into a diagram just so we can see it clearly. So I've prepared here two separate diagrams, and I've got WG on the x-axis, WB on the vertical y-axis, and then I've plotted in the 45-degree line. Hopefully that shows up on the camera. So if we were to consider, let's put low effort over here and high effort over here, then if I draw a set of ISO costs, something like this, try and draw them parallel. So these are different ISO costs, maybe C1, C2, C3. And the slope of this line is determined, is based on low effort. So it's 1 minus P, probability of the bad state conditional on low effort, divided by the probability of the bad state conditional on low effort. Okay, so that would be the slope of ISO costs when we know that our employee is putting in low effort, or when we can assume he's putting in low effort. And under high effort, these are going to be steeper, so these are quite flat. So let's draw some steeper ISO curves over here, perhaps something like this. Okay, so these would be, let's put C squiggle 3, C squiggle 2. So different ISO costs for assuming a high level of effort, and the slope in this case is going to be based on the probability of the bad state conditional on high effort. Okay? So these are steeper than these. Now, if you remember when we studied the Rothschild-Stiglitz model, we had a high-risk type and a low-risk type. And the low risk had steep isocosts, and the high risk had flat isocosts. So we need to remember this is the other way round now. It's not high risk, which is bad. High effort is presumably a good thing. So it's kind of the desirable behavior gives you steep isocosts, and the undesirable behavior gives you flat isocosts. Similar in the Rothschild-Stiglitz model, the undesirable type, the high-risk type, had the flatter isocosts, and the more desirable type, the low-risk type, had the steep isocosts. So just remember that it's the other way round now. That's why I've put this P conditional on epsilon L rather than just putting PL and confusing ourselves, because we already used that notation in a previous lecture. Now that we've developed the tools to analyze a firm's costs, let's look at employee preferences. So we're going to assume that the employee is a risk-averse expected utility maximizer, and so their preferences are represented by expected utility with a strictly increasing and strictly concave von Neumann-Morgenstern utility function. Instead of assuming that the employee has an endowment to trade, we're going to imagine that they have a level of reservation utility, which will denote underline U. So reservation utility is essentially the level of utility that this employee can guarantee when they don't accept the wage contract. Okay, so perhaps they have an offer somewhere else, and the employer is going to have to beat this offer before the employee actually comes to work. Now, regarding effort and the employee's preferences for different levels of effort, we're going to make this very simple and assume that expected utility is linear in the disutility of effort. So effectively, if an employee exerts a high level of effort, we will denote by epsilon h the amount by which the employee's expected utility is reduced. Similarly, if they put in a low level of effort, there is an amount epsilon L by which their expected utility is reduced under that level of effort. So we're abusing notation a little here by using epsilon h to denote both the action of choosing high effort and also the amount that utility is decreased when they put in high effort. Naturally, we're going to assume that epsilon h is greater than epsilon L, by which we mean that expected utility is reduced more by high effort than by low effort. Other things being equal, the employee would prefer to put in low effort. Of course, we can't assume everything is equal when effort changes, because effort has two effects in this model. The first effect is that it increases the likelihood of the good state or reduces the likelihood of the bad state. So higher effort is better in part for expected utility because it increases the chances of getting that good wage, which has higher utility than the bad wage if the good wage is no less than the bad wage, which is a natural assumption. However, high effort has a downside in that it decreases the employee's expected utility by a greater amount than low effort. So clearly there's a trade-off when the employee chooses high effort versus low effort. There's a trade-off between the effect it has on the expected utility of the contract itself and also the disutility of the actual level of effort they are going to choose. Let's go on paper now and develop the graphical tool for representing this employee's preferences in difference curves. Okay, so now let's develop the graphical tool for analyzing preferences. We're very familiar with this already. We're going to be studying indifference curves. So remember, the objects of choice in this model are what we called contracts. So a contract W has two dimensions, a payment in the good state, WG, and a payment in the bad state, WB. Okay? And while we develop intuition for this, we're just going to assume that WG is greater than or equal to WB. Okay, that kind of makes sense that they get paid more in the good state. This can be proved later, but it'll help develop our intuition if we assume that for now. So we're going to assume that decision makers, the employees in this case, are expected utility maximizers and they're risk averse, but they also take into account the level of effort. So let's write out the formula. So we're going to have the expected utility of a contract W conditional on the level of effort, which we denoted epsilon I. Now this is equal to the probability that the bad state occurs conditional on the level of effort. Okay, the level of effort affects the likelihood of the bad state. That's the stochastic relationship we mentioned before. Multiply this by the utility of the wage in the bad state. And then we do the same for the good state. So 1 minus the probability of the bad state conditional on the level of effort epsilon I, multiplied by the utility of the wage in the good state. And then from this, we deduct epsilon I. So essentially, we're going to use epsilon I as notation in two ways. It's going to denote both the level of effort and also the disutility associated with that level of effort. Okay, and remember, this is for I is either high or low, and we also assume that epsilon H, so high effort, has a greater disutility than low effort. Okay, so sometimes this is called a linear in disutility of effort model. Okay, so you could imagine, for example, a more general model. If I said something like the von Neumann-Morgenstern utility U, say the wage in the good state or the bad state, either. Well, we could think of it as kind of a bundle. I get that wage and I put in a level of effort. Okay, so in a sense, my utility is going to depend on two things. And what we're assuming is that we can separate the utility of the wage and then just deduct this term epsilon I. Okay, so it is a very kind of, it's a simplifying assumption. We're limiting the scope of our analysis. Why would we do such a thing? Well, because it's going to make the analysis so much cleaner and more simple by making this very simple assumption. And when we're in a world with just two levels of efforts and two states of the world, we're really not limiting our model very much. Okay, so what do we? Let's have a look at indifference curves, and we'll see why this linear in disutility of effort model is so tractable. So remember, an indifference curve and again, this is very, very similar to the Rothschild-Stiglitz model. Really, it is the Rothschild-Stiglitz model. We're just interpreting things slightly differently, but we're using all the same tools. So an indifference curve, if we wanted to kind of derive its slope, well, we'd start with a property of an indifference curve. So change in, or D, the differential of expected utility conditional on effort I is 0. Okay, and if you expand this total differential and then do the rearranging, exactly as we did in lecture 4, you'll find that the slope of an indifference curve, so the derivative of WB with respect to WG, okay, I suppose I could make a note here that change in expected utility is 0, to say this is the slope when utility is constant, so the slope of an indifference curve. This will be it's going to be very similar, well, exactly the same as the Rothschild-Stiglitz case. So we're going to have this odds ratio, 1 minus the probability of the bad state conditional on the level of effort, epsilon I, divided by the probability of that bad state conditional on the level of effort, epsilon I, and then we multiply by this ratio of marginal utilities. So the marginal utility of the wage in the good state divided by the marginal utility of the wage in the bad state. Okay? So this looks very similar to the case when we studied insurance and we had high risk and low risk types. And if you remember then, the kind of the worst types were the high risk types were really the bad types of consumers, and they had the flatter indifference curves. Well, here, the low effort employee is kind of the worst type. And again, they're the ones with the flatter indifference curves. So if I draw these on a diagram, I've prepared some diagrams already with our WG on the horizontal and WB on the vertical, and then this 45-degree line. So what do low effort indifference curves look like? They're going to be quite flat. So maybe something like this. They're downward sloping and convex. Okay, so something like this. That's about the best I can draw them. Okay, and then the slope of these we know is minus 1 minus the probability of the bad state conditional on low effort divided by the probability of the bad state conditional on low effort, and then multiplied by this ratio of marginal utility terms. Okay, so that's the slope of the employees. I keep saying types. It's not a low effort type. It's when an employee chooses to put in low effort, their indifference curves become flatter, and when they choose to put in high effort, their indifference curves become steeper. So maybe they look something like this. Okay, so here is a typical indifference curve when the employee chooses to put in high effort. Okay. We haven't mentioned reservation utility yet. So where does that come into this? So essentially what we're going to do, we're going to label one of these. I'll label this PCL. Okay. And what we mean by that is the participation constraint for when the agent puts in low effort. Okay, so PCL is what does that mean? Well, the curve that I've labeled PCL is essentially, so it's all of the contracts W with the property that the expected utility of those contracts W conditional on low effort is equal to reservation utility, which we denoted U with this underlined part. Okay. And reservation utility was the amount of utility that the employee could achieve kind of without coming to work. So it's like the opportunity cost of coming to work. Okay, so it's either the utility of leisure or the utility of a second best offer that they've received. So it's going to play a role in solving the cost minimization problem. For us, just for now, we'll note that this curve PCL, if, for instance, we offer if the employee puts in low effort and we offer them a contract anywhere along that curve, then they will accept it, okay? And if we offer them a contract on a higher indifference curve, so a contract on any of these, then they will definitely accept that contract. But if we offer a contract down here, okay, so this low contract, this contract below that PCL curve, well, then the employee will simply not accept that contract, okay? So they would just go and work somewhere else, presumably. And so if the employer wants the employee to come to work, this PCL curve is really the constraint that is going to be required. So we call it a participation constraint. Okay. In some books, they call it an individual rationality constraint, but we'll stick with the term participation constraint. Okay. And of course, if we do a similar thing for the employees who put in a high level of effort. So conditional on putting a high level of effort, the employee's participation constraint is different. So if they're going to accept a contract conditional on high effort, then they're going to need a contract that's either somewhere along this curve or above. Okay. And of course, this PCH would be defined essentially by replacing this epsilon L here with epsilon H. Okay, so that's the nature of the indifference curves in this model. When the employee puts in low effort, their indifference curves are flatter, and when they put in high effort, their indifference curves are steeper. One of those indifferent, in each case, there is a special indifference curve we labeled PCL or PCH. And this means that, and this is the particular curve, the participation constraint, meaning that the contract needs to be on that curve or above in order for the employee to actually accept the contract and come to work.